In this video we'll be discussing the arc length and curvature of space curves using vector functions. So let me start with the arc length. Well, it is basically the length of this space curve, and it's computed via evaluating an integral. So the arc length of a space curve is denoted capital L, and it's the integral of the length of the derivative of the vector function which is tracing out the space curve. Okay, so from some value a to some other value of t, b. So these are the two and the initial and the end points of this space curve. It could be giving rise to the same point if it's a closed curve. The length of the unit of the derivative of RT is, of course, the square root of the squared sum of its components. And as you remember, the derivative of a vector function can be computed by computing the derivative of its components. So it's simply, if its components are f, g, and h, as we've used before, you just differentiate each component, square them, add them up, take the square root, and integrate the result. So exactly f prime squared plus g prime squared plus h prime squared under the square root is what we have to integrate with respect to t, from t equals a to t equals b. So that's going to give us the length of the curve that's parameterized by the vector function RT. So it's just the integral of the derivative vector. Okay, so this can be, well, just let me give you an example. Let's compute the length of the following of the space curve, which is given by the vector function RT equals I will give you its components is cosine of t, sine of t, and t. And we'll consider t change between 0 to 2 pi, 0 and 2 pi. Okay, so first we need, in order to find the arc length, the length of this curve, you need to compute the derivative and then integrate its length from 0 to 2 pi. Pause the video and input your answer below. Okay, so I hope you paused it and computed the derivative. Component by component, we differentiate each factor, so we get minus sine of t, cosine of t, and 1 for the components respectively. The length of that derivative, the squared sum of its coordinates, is well, the sine squared plus cosine squared, that gives you 1, plus 1 squared, that gives you 2. Okay, just using the famous trigonometric identity, and taking the square root gives us root 2. So indeed, the length of the derivative vector is just root 2 for all values of t. So what we are integrating to get L is just root 2. So we are integrating a constant from 0 to 2 pi with respect to t. Well, that of course will give us root 2 times t. We can ignore the constant of integration because we are dealing with a definite integral. So this is going to give us, of course, root 2 times 2 pi for the length of the curve. So I hope you got that right. Now, in a previous video, I mentioned that the difference between vector functions and space curves are that space curves are static objects, geometric objects, which are not parameterized until you try to describe them using a vector function, which has a parameter and tells you how to go along the curve. and how to trace out the points on the curve with what speed you want to run along the curve. So that's what this parameterization does. And but there is a natural way of parameterizing a curve, which is parameterizing by arc length, by the length of the curve exactly. So as the parameter changes, goes from 0 to 1, you trace out the curve. So it goes from being length 0 to length 1, exactly by the increase of the parameter. So the arc length function is a function of t. So once you have one parameterization of your space curve, you can introduce a new parameterization of the space curve, which is called the arc length parameterization. For that, you need to compute the arc length function, which is just basically computing the length of your derivative, r prime of, now I have to choose some other letter for this. Let's say it's u. So just compute this integral from a to t now to get the arc length function. Then once you have this integral evaluated, it will depend on t. So once you have that, you can actually express t as a function of s by inverting, finding the inverse. Inverse function of the arc length function, and then you expressed the parameter t in terms of the arc length s. Substituting that into rt will give you the arc length parameterization. So that, and let me show you, well, I'll give you a question, and this will illustrate this. Let's take the same vector function as before. So with components cosine of t, sine of t, and t. And your task is to find the arc length parameterization, so this function of t of s. Pause the video and input your answer below. Okay, I hope you paused it and basically realized that you are computing a similar integral that we did here, although with instead of 2 pi being the upper value, it's t, and now we are differentiating with respect to u, just not to confuse ourselves with two t's being in the same formula. So s of t will be the integral of this function from 0 to t, this function being the derivative of rt, well, its length, really. Sorry, no, I just said that I wouldn't use two t's, so let me put u instead of t in the arguments. So we are integrating with respect to u. Now, but this length of the derivative has been computed before it's 2 pi, so we are integrating from 0 to t, and the constant, sorry, not 2 pi, root 2, with respect to u, and that will give us root 2 times t, exactly this definite integral. So we have now this function st in terms of t. Now we have to find the inverse function. So that's what we'll do here, is we'll express t as the function of s, and t as the function of s is just rearranging this formula to express t with using s, and that's just dividing by root 2, so that's 1 over root 2 times s. So now we have t expressed as a function of s, and now we can go back to our original vector function and have its parameterization by arc length. So that's parameterizing by arc length, meaning that we substitute for t this function t of s, which is in this case is a very simple function. It's just 1 over root 2 times s. So what it gives us for the components is the cosine of s over root 2, the sine of s over root 2, and s over root 2 for the 3 components. Okay, so with that, now we have a way of obtaining a natural parameterization to space curves, parameterizing by the arc length.